Okay, now let us look at an application of integration in communication engineering. For those who studies communication engineering, it is important to understand that when the information is communicated, this requires high level of reliability so that what is sent is exactly what is being received. So in this context, the performance of a communication system needs to be rigorously studied in terms of mathematical models. Actually, the channel of communication is mathematically modeled and it matches closely the realistic one. So let us write a few notes here just for understanding. For example, in mobile networks, we see that now in the fifth generation of mobile networks, we say that we require what is known as an ultra reliable and low latency communication. URLLC, ultra reliable low latency communication, or 5G and beyond mobile networks. So it's very important that we have this reliability. So in this context, the reliability of a communication system needs to be studied in terms of mathematical models. So a common mathematical model for a wireless communication system, like we have the mobile communication system. So a common mathematical model is the really fading model. So in this lecture today, we will discuss the mathematical evaluation, or we can say formulation as well, of reliability. Or we can use another word also, performance. Sometimes in some textbook we refer this as the error performance of relay channel for a digital modulation technique called multi-phase shift keying. I call this the MPSK modulation. We will see how to use integration to carry out our analysis. So the reliability or the performance measure is in terms of the error probability. That is an error that is encountered when a message is communicated between a sender and a receiver. Okay, now let's start with the mathematical analysis. We are going to write it as an MPSK, probability integral. The average probability of error in an additive white Gaussian noise channel can be found by using a conditional error probability and the probability density function of the noise channel. That is, we are going to write it like this: the probability of error for a given sample. I'm going to write it from 0 to infinity, or the conditional error probability. It is conditioned on a parameter, which I will explain after, and the PDF of this parameter. Now, this parameter denotes a communication engineering parameter, very important for the signal to noise ratio, SNR. For every bit that is communicated between the sender and the receiver. So this is what we are going to focus in order to determine the error probability. To find the average error probability over a wireless channel with relay, that is, I'm considering the wireless communication system with relay fading properties. We require the PDF or the SNR for a relay fading channel. That is, that is the PDF or the Rayleigh is actually mathematically represented as follows, where this refers to average signal to noise ratio per bit. Now we analyze further. The Laplace transform of a Rayleigh PDF can be found by using a very important statistical parameter called a moment generating function, MGF, or the average SNR per bit. That is, I'm going to write it like this. MGF of the SNR per bit, S is a Laplace transform, equal 1 over 1 plus S. This is the average SNR. For our case here, for MTSK modulation, the average error probability over a Rayleigh fading channel can be found as follows. So I'm going to write it like this. 1 over pi and integration this has already been worked out in some textbook. So we require now to analyze this further to be able to find expressions, mathematical expressions, in order to determine the probability, which is our performance measure. So this has been given in a book where A is a parameter but depends on the MPSK modulation. Now, what do? We replace the MGF or the Rayleigh here in the PE equation number, and what do we get? PE will be 1 over pi integration 0 it's going to be 1 plus 1 over S plus 1. So it will be A squared average SNR 2 sine squared theta. And this turns out to be 2 sine square theta. If you work it out, you will get it like 2 sine square theta plus a square average, so no per bit, and this works to O, which is further equal to so this becomes our integral of interest. Now, if you recall from our previous lessons that we have studied on integration, we had some integral that involves trigonometric function, but not the one of this type. In order to be able to evaluate this integral, we will make use of the table of integrals. This has already been published in some textbook. So let us look at this now. We make use of the table of integrals. So the integrals of the form integration, as you can see, sine square over sine square theta plus a square where no substitutions can be used. Like before, if you recall, we make use of many types of methods to perform integration, substitution, partial fractions, by parts. So now we will not be able to use this. So we will make use of table of integrals. You can download actually this table of integrals. The title of the book is Table of Integrals, Series and Products. So we are going to use this from the table of integrals. At equation, if you will download it, you go to equation 2.562.1. We can obtain integral as follows. So we will have it as 1 over pi from 0 to pi by 2. If you want to integrate this here, you will get it as 1 over pi what we are going to do, we are going to split this. Which can further be rewritten as this integral. And now I can do use this for our analysis. So what do? We substitute the upper limit of the integral with m minus 1 over m pi, and hence our probability integral becomes pi. So I have just replaced the limits of the integral like using table of integrals, we obtain the solution as follows. So this integral 1 over pi which is minus, which is multiplied, tan inverse this is what we get. Or we can write it also as m minus 1 over m, 1 minus, this remains the same here as above, we can write it as pi by 2 plus tan inverse cot. And then we refer to the above error probability where we add the a square, the average, and replace as c equal a square like this, where for MPS modulation in communication system, again in textbook you can find this, a square becomes a square by 2 become sine square pi by m, where m is the order of modulation, that is 2, 4, 8, 16, and so on. Hence, replace C equal the average SNR per bit sine square pi by m in the other equation and get the general equation to find the error curve. So what do we have here? When we replace m minus 1 over m, now I'm going to have it 1 minus square root. This is the parameter sine square pi by m over m inverse times cot of pi by m. Second square bracket, and finally the bracket. So this expression can be evaluated by using MATLAB or Mathematica software. So we have studied here how to use integration to evaluate the reliability or the performance of a communication system. This is the power of integral calculus. Thank you very much.